You're sitting inside a train moving at over 200 miles per hour. Outside, the world isn't moving anymore. It's streaking. Trees blur into green lines, buildings flash past before your brain can even register them. And then the train starts to turn. Not slowly, not gently, but at a speed that in any other situation would feel completely out of control. Yet inside, almost nothing happens. No violent shaking, no screeching panic, just a smooth, controlled lean. Which raises a question most people never stop to think about. Why doesn't it fly off the tracks? If you took a car at that speed and tried to turn, you already know what would happen. The tires would lose grip, the car would slide outward, control would disappear almost instantly. So why is a train, something massively heavier with no steering wheel, locked onto a fixed path, somehow more stable? Here's where things start to get interesting. Most people assume the answer is simple. Weight. The train is heavy, so it stays down. But that explanation falls apart very quickly, because weight alone doesn't solve sideways motion. In fact, the heavier something is, the more force it generates when it tries to change direction at high speed. And that's the real problem here. When something moves in a straight line, it naturally wants to keep going straight. So when a train enters a curve, it's not just turning, it's being forced to change direction against its natural motion. And that creates a powerful outward force, the same one you feel pushing you sideways in a car. Now, scale that up. Hundreds of tons, extreme speeds, continuous motion. At that point, it's not just uncomfortable, it's dangerous. Because if nothing counteracts that force, the train doesn't just feel unstable, it physically tries to leave the track. And this is where most people get it wrong. They picture the train as something that's barely holding on, as if the wheels are just gripping tightly enough to survive the turn. But that's not what's happening at all. The system isn't relying on resistance, it's built around alignment. Instead of fighting the force trying to push the train outward, the entire track is designed to redirect it. And the key to that lies in something so subtle most passengers never notice it. The tracks aren't flat. When a train approaches a curve, one rail is slightly higher than the other, not by a huge amount, just enough to tilt the entire train. This is called superelevation, but in simple terms, it means the train is leaning into the turn. So instead of being pushed sideways across a flat surface, part of that force is redirected downward into the track, and that changes everything. Because now, the faster the train goes, the more naturally it presses itself into the rails instead of away from them. It's no longer trying to escape the curve in the same way, it's being guided through it. This is the same principle you use when riding a bicycle. At low speeds, you stay upright. But the faster you go, the more you instinctively lean into turns. Not because you were taught to, but because your body is solving the physics problem automatically. The train is doing the exact same thing, except instead of instinct, it's engineered. And here's what surprises most people. That angle, that slight tilt, isn't just a rough estimate. It's calculated with incredible precision. Engineers take into account the speed the train is expected to travel, the radius of the curve, and the forces involved. There's an exact angle where everything balances, where the outward force and the tilt of the track cancel each other out just enough to create stability. But here's where it gets even more interesting, because trains don't all travel at the same speed, and that creates a problem. If you design the track perfectly for one speed, it becomes imperfect for another, which means the system can never be truly perfect. It has to be optimized, and that leads to one of the most overlooked truths about high-speed rail design. It's built for consistency. And that decision affects everything, from how curbs are shaped, to how passengers experience the ride, to how safe the entire system feels, even at incredible speeds. And once you start seeing it this way, you realize something important. The train isn't defying physics, it's working with it, in a way that's almost invisible.
But here's where things become even less obvious. If tilting the track solves the problem, why not tilt it more? Why not design every curve so trains can go even faster without any sideways force at all? It sounds logical, but this is where reality pushes back. Because not every train moves at top speed. Some are slower, some are stopping, some are accelerating. And when a slower train enters a heavily tilted curve, something strange happens. Instead of being pushed outward, it starts to feel like it's falling inward. The same system that stabilizes high speeds begins to work against low speeds. Passengers feel pulled toward the inside of the curve, cargo shifts. The ride becomes uncomfortable and, in extreme cases, unsafe. So engineers are forced into a compromise. They can't design for maximum speed alone. They have to design for a range of speeds, which means choosing an angle that doesn't fully cancel the forces, but balances them well enough across different situations. This is where most people get confused, because we tend to think engineering is about perfection, but in reality, it's about trade-offs. And high-speed rail is one of the clearest examples of that. The track isn't perfect for any single train, but it works incredibly well for most trains most of the time. And that's what keeps everything stable. Now here's another detail that quietly makes a huge difference. High-speed trains don't just rely on tilted tracks. They also rely on the shape of the curves themselves. Whenever possible, curves are made very wide, not sharp turns, but long, gradual arcs. This reduces how quickly the direction changes, which reduces how intense the sideways force becomes. In other words, the train isn't being forced into a sudden turn. It's being gently guided into a new direction. And often, there's a transition section before the curve even begins. A subtle shift where the track slowly tilts and bends, so the train never experiences an abrupt change. Most passengers never notice this, but their bodies do. Because sudden movement is what creates discomfort. Smooth transitions are what create the illusion of effortlessness. And that illusion is carefully engineered. But there's still one more piece that ties everything together: the connection between the train and the track. Unlike cars, which rely on rubber tires and friction, trains use steel wheels on steel rails. At first, that sounds like a disadvantage: less grip, less control. But here's the surprising part. Trains don't need as much friction because they don't steer freely. They are guided. The wheels are shaped in a way that helps keep them centered on the rails, and the flanges, the inner edges of the wheels, act as the final safeguard. If the train shifts too far, those edges make contact and prevent derailment. So instead of relying on grip alone, the system uses geometry, shape, constraint. Everything is designed so the train doesn't have to fight to stay on track. It naturally stays there. And when you combine all of this, the tilted rails, the carefully calculated angles, the wide gradual curves, the smooth transitions, and the guided wheel design, you start to see the full picture. The train isn't on the edge of losing control. It's operating inside a system where control is built into every detail. So, no, a 200-mile-per-hour train doesn't fly off the tracks. Not because it's lucky, not because it's barely holding on, but because every part of its environment has been designed to quietly prevent that from ever happening in the first place. And once you understand that, you start to notice something deeper. This isn't just about trains. It's about how the most reliable systems in the world work. They don't rely on last-second corrections. They don't depend on perfect conditions. They are designed so that failure becomes unlikely from the start. So, the next time you're on a train moving at incredible speed and it glides through a curve without effort, remember this: you're not experiencing something simple. You're experiencing thousands of small decisions working together so seamlessly that they disappear. If you enjoyed this, leave a like, share it with someone who's never thought about this before, and subscribe for more. Because sometimes the simplest things hide the most misunderstood truths.